All right, so remember, we talked about how we would build these Legendre polynomials out of our solutions to that differential equation. And I said, I'm just going to write down for you what a few of these look like. So we're going to continue our discussion of Legendre polynomials. And sort of in general, P sub n of x solves 1 minus x squared y double prime minus 2x y prime plus n times n plus 1 y equal to 0. It's one solution out of your fundamental set. Sort of how when we first learned how to solve second order equations, we did that reduction of order where you assumed you had one solution. This could be that one for you. We're going to have P0 of x, is equal to 1. And that one's going to solve like 1 minus x squared y double prime minus 2x y prime plus 1. Oh, wait, sorry, this is for 0. So plus 0 times 1 times y, so that's just 0. P1 of x is equal to x, and that one's going to solve 1 minus x squared y double prime minus 2x y prime plus 1 times 1 plus 1 is 2 times y, so just plus 2y equal to 0. P2 of x is going to be equal to 1/2 times 3x squared minus 1. That one's going to solve. All this stuff stays the same. It's just our n value that changes. And so for 2 times 3, we're going to get 6. Y equal to 0. I'm going to stop telling you what they solve and just write out a few more of these. P3 of x is going to give us 1/2 times 5x cubed minus 3x. P4 of x is going to give us 1/8 times 35x to the 4th minus 30x squared plus 3. And let's do one more. P5 of x is 1/8 again, I think, times 63x to the 5th minus 70x cubed plus 15x. And so the polynomials go out longer for every higher power you take, cut off after x to the 0, x squared, x cubed, x to the 4th, x to the 5th. And they're all going to be just one given solution to this type of differential equation. And they're also going to have some cool properties. So remember, we started this whole conversation by saying that we would only consider our solutions, and so we can only consider these polynomials over that special bound of x. X has to be less than 1. That's the radius we can think about here. Any more than that, and we've sort of gone into a bad region. And then they have just some neat algebraic properties. So P sub n of minus x is just minus 1 to the nth power of P sub n times P sub n of x. And then P sub n of 1 is 1. So P sub n of minus 1 is just minus 1 to the nth power. And then you're going to have that P sub n of 0 is 0 for odd n. And then if n is even, you're just going to have that the derivative is 0. So P sub n prime of 0 is 0 for even values of n. And then, let's see, there's this sum property, n plus 1 times P sub n plus 1 minus 2n plus 1 times P sub n times x plus n times P sub n minus 1 is equal to 0. So you can use that to solve for P sub 6 of x given all the others. So sort of if you have p sub n minus 1 and p sub n, you can follow this formula to solve for the next order up. And I would show you that example, but I'm concerned that I've already given you too many videos for today. I'll show you that example just in case you don't believe me, but then you can skip this example if you don't want to. So let's just say we want to find p sub 2 of x, given that p sub 0 is equal to 1 and p sub 1 is equal to x. Then we know the formula, p sub n plus 1 times n plus 1 minus 2n plus 1 times p sub n times x plus n times p sub n minus 1 is equal to 0. So when we want to find p2, we're going to plug in n equals 1. That's going to tell us p2 right there is equal to 2 times that minus 3 times p1 times x plus 1 times p0. That should be equal to 0. So p2 would be equal to 1/2 times 3p1 times x minus p sub 0. So it's 1/2 times 3, p1 is x, so 3x times x is x squared minus 1. And then if we go back here, we found p2 is 1/2 times 3x squared minus 1, 1/2 times 3x squared minus 1. So that's just showing that that kind of recursive relationship works. And yeah, that's sort of the neat thing about these polynomials. They show up in other applications, sort of like numerical approximation would be a place where these show up if you take that kind of class in the future. So that's why it's neat that they come out of it. Really, the most important thing was finding solutions here. So I'll emphasize that in the conclusion, though.